اليوتيوب انا قاعد اسوي بودكاست.
وهذا قد مسجل في البودكاست ها؟ يقعد.
Trouble is, I know which is shocking. Actually, I have an American friend in Antwerp, so I said, "Well, tomorrow let's meet this afternoon." And I came along with just a partner. He came along with a competency set and a strainer. Like this American guy showed me out because he knows how to make tea properly. And then we do what we call Ouni's team, which is we used to have a really strong tea in hard place. Oh yeah, there's that as well. And tea means different things depending on which part of the UK you're from. So they say we have it's a meal as well, but it's unclear whether it's supper or dinner or
Did you guys ever see
Well, I think that's it. I think recently we established a concept overseas of distribution of notion tea. So you have two disparate groups that go back to the United States or something based on that. That's the freedom of tea-based tea.
game programming courses? Any, you get any publications?
I don't
We had a guy in my undergraduate he dropped out of the CS program halfway through to go to digital. He learned that he's been working on like 7 songs. Everybody go when you grab Do you ever get students that don't realize Just starting with the easier for you to see. I love the little Portuguese kids. So, you know, we have
Okay, I think we're already 6-7 minutes late, but we have some movement at the end. So let's start this session. The first speaker will be Mohamed. Wiem, can you pronounce Wiem? Yep. Yeah. Okay. And we're going to talk about many objective software engineering using preference-based VA. So very much follow what we talked about before. Go ahead. Okay. Good evening, everyone. Everyone listens to the microphone. Can you hear me now? Good afternoon, everyone. I hope that you enjoyed your food. And today I'm going to talk a little bit about my early investigation in the many objectives of engineering using the reference-based relational algorithms, specialty in case study in software manufacturing. Dr. Jack has already saved my life by explaining the many objectives of optimization. So I'll try to emphasize it from, of course, from the AI perspective. I'll try to show the next one about how we can use it also, and we need it also in software engineering. So the talk will be basically going through the context and problem statement, we'll talk a little bit about the many objectives of refactoring and utilization and conclusion and the future work. So based on this morning's classification of the good, the bad, and the ugly, we end up being the bad guys. Or let's say we're working with the bad side. But at least our intention is probably good because we try to tackle the problem of optimizing software quality by detecting or also correcting the design defects, which are usually, they are bad code fragments, which are usually and mainly introduced during the initial design or during the maintenance level of the software. They usually make the software hard to understand, hard to maintain, and they have, of course, very bad, they have also really adversely affect the development of the software. So one way to fix this problem is by using the refactoring. As we all know, the refactoring is the art of restructuring the structure of the source code without altering its external behavior. It can be classified mainly into the manual refactoring, the semi-automatic refactoring, and full automatic refactoring, which also be used in this context. Search we use in search-based refactoring, which represents a semi or fully automatic refactoring driven by a meta-heuristic search, which is trying to optimize some specific quality attributes, and then we try and address, of course, the problem of automating design improvement. So if we look at the existing work, we'll see that this problem was already tackled since 2003 by Dr. Mill, which was supposed to be here by the Kessentini, so I hope he gets well soon. He used the semantic annealing to tackle the problem of the hierarchy inside the Java classes. He was optimizing two metrics, which were the available and the inherited methods inside the classes. That also work. We have also another work which was done by Dr. Chang. She's a professor in MSU, so she's an hour from here also. And she used the genetic programming to tackle the problem of the introduction of design patterns inside the source code. And she also used actually the aggregation of the Q model quality attributes as a fitness function for her genetic programming. And since you know that, as Mohamed said, that the problems in software engineering, search-based software engineering, they are mostly multi-objective, so it was normal and natural and regular for us to switch from the mono-objective approaches, which are mainly using the aggregation of many metrics to improve the internal structure, into the multi-objective approaches, which have the variant optimization, which the term that was used mainly by Harman in 2007 when he described the problem of finding the compromise and the trade-off between the CPU and the standard deviation standard deviation in the methods and the losses as a trade-off, as a quite optimal problem. And then we have also the work of Ouni, when he was trying to add the semantics preservation along with the structural improvement of the source code, and he tackled that as a multi-objective problem, and he used an SGA3 for that. So these two works, they see the refactoring as a multi-objective optimization problem, and they, of course, they produce a better trade-off solutions compared to the mono-objective solutions. And the number of objectives in this case is slightly limited. At this level, we can probably have two questions. The first question is, why do you have the number of objectives being limited? This question has been answered by Feldt earlier. The second question is probably from software engineering perspective. Why do we need to have more objectives in multi-objective refactoring? So this actual question can be answered if we look, for example, at the spectrum of 4 popular design defects, which were the blob, the spaghetti code, the function decomposition, and for example, the space fragment knife. We can see here that, for example, for this design defect is a composition of multiple symptoms such as the localization, the large class, beta class, etc. So, but if we are able here, for example, as a detection problem, if you want to make sure that the code element as a class is a blob, we have to make sure that these symptoms exist in this blob to, of course, to avoid having false positives. But the intuition here that if we are trying for example, to fix this problem as a correction problem, we don't actually need to fix all these symptoms together. For example, we can try to fix the data class inside the globe to make this globe is no longer a globe. So the existing work for Kalyanmoy and Marouane, they usually try to tackle only one as a correction problem. They try to tackle only like a limited number of metrics. For example, if we look at the coupling and collision, they're mainly working on how to minimize the number, for example, to distribute the number of methods in a class. So one of these, for example, the shortcuts and long division can be optimized. But if we try to scale and we vary the number of metrics that we use to optimize the refactoring that we are trying to give, we might be also able to tackle other symptoms, and this might help us also detect, or fix these kind of the defects inside the code. So this is from where we started by trying to have multiple, metrics in our taken as objectives in our optimization in order to be able to cover mostly all the symptoms of these design defects. But the other limitation that we can have is if we try to use the existing multi-objective techniques in our optimization, we might end up falling in this trap, because we notice that when you use the multi-objective techniques the way they are, we have a problem of the dominance of all the solutions being dominated. As we notice here, if we scale, for example, if we use here, So if we use here, for example, 5 objectives, we notice that since the early generations of the evolution, we have already a huge number of Pareto equivalent solutions. Here already, for the case, for example, of 5 objectives, we figure out that 80% of the solutions are already equivalent since the second generation, which makes, of course, the determination, of course, it reduces the determination of the searchability, and this is going to increase the objective space dimension, and then, of course, it will be also hard to visualize and understand the correlation between solutions distribution. So this is one of the problems that we face when we are actually, scaling the number of objectives. So multiple work has been produced to try to fix this problem. One of them is, for example, the objective reduction, where we try to study the correlation between the objectives and try to reduce, by trying to detect the conflict, the degree of conflict between the objectives, and try to reduce the conflict by have a subset of objectives, also to cluster these objectives together to reduce the number of objectives, which is basically trying to take the problem from many objective level to the multi-objective level. We have another way to do it is by decomposing the problem into subproblems to generate, to have assign these kind of subproblems into different derivations, and then generate solutions and compare between these neighboring solutions. And these, of course, this technique is usually problem dependent, so it's hard to make it generic. We have also the preference-based optimization, which gives the hand to the decision maker to decide about a preference and the search space. This preference can be a set of reference points that he injects into the search space in order to help or to create a new partial order for the Pareto equivalent solutions to merge into what we call a region of interest. So for that case, we are using this third technique, and we call it the preference-based evolutionary algorithm, of course, oriented for the refactorings. So our goal is to come up with the best set of refactorings, which is able to satisfy multiple metrics in the hope of detecting more symptoms of the design defects or different symptoms of the same type of a design defect. So in this case, we will be able to minimize the coupling, maximize conversion, minimize complexity, etc. And the way this works is basically based on the NSGA2 with a slight difference on the way we do the selection pressure. So we'll have, of course, a back population, which is basically a set of solutions which are a set of refactorings. We'll apply the crossover application to get into the offspring population, which is going to be, of course, applied to the evaluation circle in order to have our fronts. These fronts, when the number of objectives is more than 5, will become basically one front. So this gray zone might be the whole zone. For the case of many objective optimization, we have many objectives, like the number might be like more than 5. Then one way to be able to fix this is by injecting what we call like a reference point, which is designed by the developer. This reference point might be the new partial order for the solutions. For this case, we'll be able to establish between the solutions that are perfect for the developer, and then we can continue our work into creating these kind of fronts, and then applying the grounding distance for the diversity to come up with a new generation for the next generation. So to give a quick example of how it works, for example, if we consider this set of solutions as our final generation. If this is our operating front, I'm not sure if it's clear or not. So if we're able to, for example, inject our first point early in the conversion process, we might end up having something similar to this MDM, which represent our solutions to the region of interest. And by this way, we'll be able to classify and be able to sort these solutions and end up having solutions that are close to what the developer wants. So in our research questions, we try to answer basically two questions. The first one is to what extent the proposed approach can correct the design defects. This is where we'll try to show our results of our technique and design correction. And then the second question is how does the proposed TMO approach perform compared to the classical multi-objective technique when we use a high number of objectives. So for the settings we basically used 3 open source projects. We know already the number of defects. This number of defects were used by the Poulding, which has, or used by the same authors, which defined the spectrum of the blob, the spaghetti code, and the function location on all these defects that has been, they were being defined by the same authors, so we have respected their way of detecting these defects, so we can also be able to validate this work. And then we have defined the DCR, which is a defect correction ratio, which is the number of perfect defects divided by the number of defects applied for the refactoring. So this is the first result that we get. The first result shows that this is our result for the number. This is the axis. The x-axis shows the number of objectives that we have, and the y-axis shows the number of corrected defects. So as you can see here, when the number of objectives is almost 2 to 3 to 4, we can see they're almost equivalent, NSGA2 solid and PMO. And then once the number of objectives exceeds 5, then we can see a considerable difference between the detection in NSGA3 and in PMO. And then, of course, this can be explained by the fact that the selection pressure of NSGA2 gets deteriorated because of the dominant variable equivalent solutions when the number of objectives is higher than 5. So for the second question, we can see that in this plot when we have 7 objectives, in this case these are the objectives, and this is our reference points. These are the aspiration values that the developer has introduced for his preferred solution. And then we can see that for NSGA2, we can see that we have a Pareto font with very high random values, while for our PMO we were able to slowly follow the reference point and come up with solutions that are personalized based on the values that the developer has introduced. And this is to give you the different distribution of detection, different design defects among these three projects, which are Exercise, Refactoring, and Touch. And you can see that we're able to detect mostly out of them, especially for the spaghetti code. And then we had some promising results using this preference-based technique, which we were able to detect more defects when we scale the number of metrics based on the number of objectives. And then we'll be able to have a preferred variable equivalent solutions. And then we may also be able to have possible decision makers with no agreement in case we can use multiple reference points inside the source space. But the big challenge should be always this research question I was unable to answer. How is the minimal number subset? What is the minimal number of reference points that is needed to detect a specific code smell? For this question, I'm still working on it. It's really tough question. Thank you.
Questions, comments? Yes.
So I enjoyed your talk, and I hope I'll phrase my question properly. I'm interested in your reference point and getting it from the user, and maybe you could show that graph where you had the your Pareto fronts right there. So I can imagine that someone might have a little bit of difficulty explaining that function to you as the reference point.
Right. As a developer, you might be able to know that if we are dealing with the coupling, we want to, for example, minimize the coupling. So the choice of these values is I'm going to run these different objectives as single objectives and try to see when I vary the number of generations of population, what is the best value that I can get in terms of coupling. The same thing I would take for the original one, I'm trying to maximize it. The same thing with the complexity of trying to minimize it. And then this aspiration value will be my ideal solution that I might get. Usually the ideal solution, as I mentioned, might not be even feasible, but we'll try to get as close as possible into it. So this is how we might be able to help the solutions in the search space to get close and to this reference point if we inject it already on the reference point. So it's kind of, as a developer, you have a knowledge about the domain. So you will be able to know what is the area of interest that your solution might be in, so they may be close to your preference.
In Dr. Deb's example, being able to say I want a $20,000 car and I have an 80% confidence that I'm able to achieve that, to me is quite different than having all of these different dimensions where you're asking the developer to give you some, I don't know, maybe ask them to order these for you in terms of importance, or this maybe goes back to Julio's comment on visualization. I just see this as a real challenge and also an interesting research problem.
It's a very interesting challenge because trying to get close to this reference point is, of course, it's sometimes feasible, sometimes it's not. And based on these solutions, you can check that these solutions, at least they are trying to be as close as possible to your reference values.
My question is, how do you get those red lines defined?
Actually, the developer can take these objectives as single objectives and he can run them and then decide about the value as a threshold. Like if we are able to, for example, minimize the coupling by this value, by this much, for that specific problem, with using, of course, for that specific project, then when you are trying to extend this work and trying to detect or to add more objective functions into that, when correcting that specific, when you are, for example, taking the coupling, you can know that by running a single objectives, you will have this value as your best value. You will do the same thing with all the objectives, and then you'll get a different set of thresholds that you can use as an aspiration value or level or aspiration vector to insert as a reference point in your search space.
There is several strategies to find this reference point. So there is some techniques that try to say you need to give us the reference point before the execution of the optimization, which is very hard, as you mentioned, to find. But there is other technique that they try to define this reference point in an interactive way. So you start executing your algorithm, you get some results, you see the solutions and their fitness function value, then you can come up, you'll say, I want solutions similar to this. But also there is ongoing research to learn the reference point, maybe from examples of good solutions. So as you mentioned, it's still like...
Yeah, the MCDM literature has lots of ways to find it. There's sometimes pairwise comparison, and then they form an HP, multiple hierarchy process, and then you see the ranking of different objectives. But then again, the question is, once I have the ranking, how do I set one value? So, as you said, it's just a matter of research still, but there are certain ideas out there in the literature to get there. Any other question? Comments? I had one. It's not clear to me. So you have a reference point, and then you are creating some more points around it.
So I'm trying to get my query to be as close as possible to that reference point.
No, in your algorithm.
Yes.
The reference point is supplied at the beginning, right?
It can be supplied at the beginning, or it can be introduced later. Because the developer might see the values and
then notice that you are creating some points around it. Is that or yeah, I understand it properly?
No, that's how.
Go back to this algorithm where we're describing the NSGA2.
No, the original interest. These
points?
are the solutions in case because the solution is for the green ones are the ones when we use NSGA2 without the use of reference point, and for the blue ones is actually the same results but with the use of NSGA2.
So that's another optimization.
Yes, it's the case when we are using the reference points.
Okay, and then you introduce those in NSGA2.
Yes. No, we are actually introducing the reference points when we are using RNSV, this is how we get the same, the same, for the same problem we can get this.
So you're trying to show that if you use the reference point methods, you don't find the whole.
Yes,
thing
you will
set.
find only a set, in the area of interest.
There's always a correlation between the symptoms of design defects and quality metrics.
Yes.
So is it easier maybe to understand from the developer his preference in terms of what types of defects he wants to fix, instead of just discussing with him like his preference in terms of metrics? Because there is several studies that try to see the correlation between the metrics and the different types of defects. So is it maybe easier to use that?
It will be the case, because if we know exactly what is the preferred defect that the user wants to detect, then we can know what are the symptoms that define that kind of defect. If you look back at this picture, yes, if I'm trying to detect the spaghetti code, I would know that the spaghetti code can be characterized by the no inheritance, by the no methods, by the no method parameters. So if I know ahead of time these symptoms for this specific design defect, then I can choose the right, metrics that might change these symptoms. For example, I can, instead of having this no inheritance, I can just optimize the inheritance to be able to fix this kind of design defect. So the choice of the metrics to be used as objectives can be also personalized and customized based on the type of defect that you want to fix.
Okay, so let us thank our speaker once again. Next paper will be presented by Simon, and the title is The Automated Generation of Comprehensible XML Text.
Okay. Well, good afternoon. My name is Poulding. I'm from the Bechikh Institute of Technology in Sweden, where I should note it's much warmer than it is here in Detroit at the moment. I think you've got a whole winter by mistake. So, first of all, I just want to sort of outline the problem we're trying to solve in the work I'm going to describe this afternoon. What we want to do is generate, it's based in software testing. And what we want to do is to generate some complex test data, as in we're going beyond just generating integers or a series of integers. We're generating complex test data, in this case, XML test data. Why XML? Well, it's quite a common format which is used in systems. We're working with a company who's using XML as well. And this process of generating XML test data has been done in the literature, but what we want to do is two things. We want to automate the end-to-end process, but probably most importantly, we want to optimize the properties of the test cases we're generating after this process. So now what I'm going to cover today, we're building on some existing work that Robert, Feldt, my collaborator, and I have worked in this area. We have a testing framework called Gödel test, and in this work we've extended Gödel test to work with XML. So I'm going to describe what that extension entails and also give a summary of what Gödel test itself is. We've also shown that we can optimize properties which are useful in terms of testing of test data that we generate by this method. And in particular, we showed that we can use a technique called Monte Carlo tree search, which is actually an algorithm used in gaming. And we want to discuss that and how we can extend that again to look at how we can generate XML which is comprehensible to the tester, especially if the tester is the human oracle. How do you reduce the whole human oracle test cost by actually generating test data that can easily understand and predict the output which should occur. I'm going to take both those strands together and talk about how we, a case study where we've actually applied it to MathML, which is a XML format which is used to display mathematical equations, for example, in web browsers. And we're going to also look at how that, what kind of coverage we achieve on a particular piece of software which takes as input MathML called JUpit. So I'm going to start off by giving an overview of some existing work in the Gödel test framework, so that I can tell you how we build on top of it to generate XML. So Gödel test is, it uses as its heart generating programs. So these are non-deterministic programs where there's a number of choices which can be made, normally by sampling from a random distribution of some kind, and that will affect both the output which comes out of the program, as well as the path that is taken through the program. So the idea is that you write a generating program which encompasses the input domain of the software that you want to test. And then you can use that generating program to generate your test inputs. But we wanted to go further. We want to actually control the type of test inputs which come out of it. So we have something called a choice model, and I'll talk about the choice model in a moment. So in terms of the generating program, this is a really simple one, and I'm going to go a bit computer science here by looking at a very abstract problem, which in this case is generating general trees. But it's an easy thing to explain, but the concept is true for more concrete test types, such as XML test data. In this case, we have a very simple generator program. It's actually written in a language called Julia, but we're not limited to testing software written in Julia. In this case, it's generating a tree by a recursive call saying a tree consists of a label, and there's what we call a construct called mob, which says you can have 0 or more subtrees of your current node. And we've also, in this case, we've labeled it, but we're going to ignore the label in a moment, by just choosing an integer between 1 and 9 to label each node. So this simple recursive statement can generate a whole range of general trees of arbitrary depth, height, and so on, by just controlling what decisions we make at particularly the mold construct there. So for example, if I choose a sequence, so each time it comes across the mold construct, as it recursively calls, it chooses, the choice model provides what we call Gödel numbers of 2, 1, 1, 0, 0. You get a tree which looks like this. It's quite a thin, tall tree. But instead, if it has another different sequence, we may get a much larger tree, which is also much wider. So it means that this set of Gödel numbers, which is called a Gödel sequence, which is supplied by the choice model, is really a description of the type of test data that we want to get out, which means we're abstracting away from the actual generator to just a sequence of integers, and we can apply all our optimization tools to the generation of that sequence of integers, and then have the properties of the actual output the way we want. So I said we want properties in a certain way, and obviously that depends on context. So, for example, if I was doing performance testing, I might consider an intrinsic property of the test data, such as some sort of size metric, such as how tall a tree is, how many nodes it's contained. That would be useful for performance testing. And that's actually surprisingly hard to do. If somebody says to you, give me some trees which consist of 10,000 nodes, yes, you can generate one tree, but generating a diverse range of trees with 10,000 nodes is surprisingly difficult to do. And we've shown in previous work how we can do that. Of course, you then have the normal extrinsic properties. So in this case, it may be that the purpose of my testing is just to find faults in the code, in which case the extrinsic property I want is coverage perhaps of the search statements or branches or some other structural element. So really the Gödel test is more than just the choice model of the generating program, it's this optimization step. So what we do this dynamically by, we generate some output from the generating program, we see what properties those outputs have, and we use that to optimize our choice model. So how do we extend that to generating XML? Well, the kind of basic framework is there, and initially when we went through this work, I started to create some generators by hand for some very simple XML types. Then really, very quickly realized that's a non-trivial job. What you want to do, you want to automate that process of going from some specification of the XML to the generator itself. So the specification language we chose, there's a number out there, but we chose one of the most general ones, which is XML schema definition. So in this example, this is just an example of how XML schema definition looks. At the top, we have some XML, which is just from a simple a catalog or library, which just shows a particular book. And then down below, we have the XML schema definition, which itself is XML, which describes what can be contained within that book element. So in this case, it says it's a sequence of elements which are title elements, plus 0 to as many as you want authors elements, and then an attribute called imprint, and by default that may or may not be there. And it also tells you what types of element have. So XML schema definitions are very rich, and in fact I've only shown the part related to the book element. The full description of how the parts are related to all the other elements like author, first name, and title, and so on, describing what format that could have. So this actually translates very neatly into generator programs. We look through the schema definition, and we create rules about how to construct XML from that. And it's very obvious that there's a number of choice points in our terminology which crop up. For example, whether or not we have the attribute, or how many authors there are in a particular book element, and then also the strings, which are the first names, last names, and title, and so on. So in fact, we end up with this kind of process. So we start with an XML schema definition. We've then written what we call a connector, which takes that schema definition and automatically creates a generating program. So there's no manual writing of a generating program. And then we apply the existing Gödel test framework to that to generate test inputs. So I said the important thing about Gödel tests is that we can optimize the properties that we want. And in this case, we want to optimize for a comprehensibility property, and I'll explain why we came to that conclusion. But first of all, I want to talk about how we do that optimization. So we found that one particular method is called nested Monte Carlo search. And it's a form of Monte Carlo tree search, which are search techniques often used in for the automated player in games. And the way that nested Monte Carlo tree search works is, I'm going to describe this in terms of a game, then map it onto how Gödel test works. The way it works is that as at your current game state, so nested Monte Carlo search is usually used in patience games. So think, because you're playing some kind of patience game, and then you've got 3 possible moves. So the way that nested Monte Carlo search says, well, I'm going to evaluate each of those moves in turn. So what I'm going to do, I'm going to take the first move, and then I'm going to simulate what would happen if I take that first move. And obviously there's a massive explosion of possibilities as you go through. So it actually takes one single random simulation. So it says, well, I'm going to take that first move, and there's 3 possible moves coming out of that. Okay, here's this 5, I'm going to pick one at random. Then there's 2, I'm going to pick one at random. And here I've reached an end state of the game. So I might have won, I might have lost, it might be stalemate. There's been some kind of metric that I can apply to this end state. So say it has a score of 0.7, and it doesn't matter what that means for the moment. And in this case, the simulation has just been random. I've just picked random moves as I've gone through. But in fact, what you can use is actually nested Monte Carlo search to actually do the simulation, hence the term nested. But in this case, we're not going to do that. Then you can do that for the other 2 states, and you can end up at an end state, and again, you score that end state and how successful that is to you. So in this case, say 0.9 says that's a really good end state. That's probably the move you're going to make. Well, obviously, we've only made one random simulation, but it turns out that in many cases, that one random simulation, although there's a lot of noise in that, it's a random simulation, the signal you get back about how good that first move is often enough to direct you in the right way. So we want to apply that technique to Gödel tests, and how do we do that? Well, if you think about each possible choice point that you come across as a node in the game tree, and your moves are choosing a Gödel number for the next choice point, then it maps onto the nested Monte Carlo search paradigm fairly well. So in this case, you can see that we're starting from a state where we have three, at the next choice point, we have three possible moves. So say this choice point is the number of sub-trees a particular node has in our general tree. It can have 0, 1, or 2, and then it can make further random simulations from that to get to an endpoint where we've built a tree and we've stopped, we can't build any further. Then depending on what our desirable property of that test data is, we can actually score that in some way and use that to decide which of that first moves we make. Then having made that first move, we then repeat that process all the way through until we end up with a piece of test data. We've shown in previous work at Gecko last year that that's a very effective process. We end up with minimal, with fairly low computational cost with test data which has the properties that we want. So what is the property that we want in this case? Well, I'm going to argue that one of it's to do with comprehensibility and in particular the nature, the size of the XML that you get out. So here I've got some very abstract XML. I didn't want to put up the very small font what it is. So say you've got a test set which achieves a certain amount of coverage, and it may be that one test set does that by having 3 separate, fairly small test cases. And the other test set has this very large piece of XML which achieves the same coverage in one test case itself. Well, it might be that if the oracle is a human, i.e. a human engineer has to say, predict what the output is and decide whether the software is actually given that output. It's possible that the example on the right-hand side is less suitable, because it's much harder to mentally understand what's going on and predict correctly what the output is. It's going to be much easier to have a series of small test cases. So we're going to argue that, for our sake, the comprehensibility metric we're talking about is to do with the size of the XML that we're getting out. So we chose this comprehensibility metric, which we're not claiming is all-encompassing, but we think is one possible take that you could have on it. So what we do, we count the structure of the XML, we count the features which we think add to its complexity. So obviously adding a new element adds to the complexity of XML, adding a new attribute does, and adding a new text node, i.e. the actual values between the beginning and end of an XML element. We have this fitness function at the bottom, which I'm not dwell too long on, but basically we looked at the ratio between the actual number of elements, actual number of attributes, actual number of text nodes, and a desirable target which the engineer, the test engineer would set based on what they think is going to be most comprehensible. We looked at the ratios because there could be very different numbers, so we want to normalize it by a ratio, and then we used a log function because we want to say that perhaps if it's half the target size, that's just as bad as being twice the target size. It also has a useful property that we very much penalize cases where there's no elements or no attributes or no text nodes, and that's useful for our particular domain that we're talking about in a moment. Okay, so I want to finish up by saying, well, how do we apply Gödel test with this XML extension, this comprehensibility metric, to a particular case? And in this case, it was MathML. So MathML is, we use the 2.0 version. MathML is a method for defining mathematical equations and also describing how they're presented. And we focus on the latter half of the specification, which is how to present it. You would present this, for example, in a web browser. It's XML, and in this case, you can see it describes properties such as variables, such as when you want a superscript or subscript or a fraction. Also describes things such as display properties such as color and so on. And it's a very rich specification. It's very long. There's a lot of things you can do with it. We also chose MathML because, in fact, there's already a manually derived test set which we use for comparison. This is from W3C. There's 208 manually generated test cases. So we use that we will use that later to compare coverage. But it also was a way that we could objectively set these targets for a number of elements, attributes, and text nodes. We did that by looking at this existing test set and calculating the mean number of elements, attributes, and text nodes. And that was some of our objective score. So what were the results of this? Well, we have a number of objectives here. We want to automate the entire process. We want to improve comprehensibility, and in a moment I'll talk about coverage as well. So in terms of the process, automating the process, well, we could automate it, and it was a reasonable automation. So we went from a schema definition to a Google test generated in about 5 seconds, just on a Mac laptop, and then to generate each optimized test case, and a diverse range of it, took just over a second per input. So we generated test sets which are the same size as the W3C set of 208. And if you work out, that means in under 5 minutes, we can in theory go from a schema definition to a test set of comprehensible test cases, which match that schema definition. But of course, that's the idealized world. In reality, you don't do that. What happens is you find a lot of issues during the way, but this is in fact the testing process. So, for example, when we did this, we found the connector which goes from the schema definition to the Go test generator actually raised a warning saying there's part of the schema definition which is never exercised, which can never be found. We found it was a typo in the schema definition. So we corrected that. And that means it's not our schema definition, but it's obviously been there all the time. Then when we looked at some of the XML generated from that process, we found that, for example, there's a color attribute, but the schema definition didn't define actual valid colors, it just said it had to be a string. So it wasn't a complete definition, so you can tidy that up to some extent. So you find another one with the schema definition. And then in fact, we actually found some bugs in software that we use, in this case, Euclid, where in fact there was a certain element in the schema definition which would cause it to crash every single time. We find another ones like this. So yes, this process also discovered a lot of bugs, both in the definition and the software in the test. But it also enabled us to complete a test set which we could use, for example, for regression testing after that. So I said the other goal was around comprehensibility, hitting these targets for the number of elements, attributes, and text nodes. And we did a comparison between a Go test generator where we did no optimization. We essentially let it generate at random according to some sensible defaults, distributions, and also optimized using nested Monte Carlo search. So a plot of these is violin plots where the width at each point shows how much of the distribution is at that point, and the red dots show the target values. So you can see on the unoptimized side, there's a lot of cases where there's no text nodes. There's a lot of cases where there's many more elements and attributes than are desirable given what the manual test set looked like. The zero text nodes is a particular concern because it means there's literally no output. There's no text nodes, there's nothing to display at that point. So that's quite a big concern. So when we optimized using nested Monte Carlo search, we did better, but not that much better, to be honest. So one thing is that we avoided a lot of the zero text nodes, and that may be partly because we chose by design what our fitness function looked like. We did pretty well in terms of attributes. The body of the distribution is around the attribute target. But it's very noticeable that we didn't manage to get anywhere near the elements target at that point. We haven't really discovered in detail what the reason is. One of them, I think, is though that the XML is very complex. The XML schema definition is very complex. There's 200 choice points, and so it's quite a hard optimization problem in this sense. But also, each element has lots of attributes. So it's very easy to choose the number of attributes correctly when you're doing something like nested Monte Carlo search. Much harder to get the number of elements right. So I think it went pretty easy targeting, which is attributes, at the expense of elements. So maybe redefining our fitness function in some way. Finally, we had a look at coverage. And this was an interesting decision because at no point have we optimized for coverage in any sense. We've just optimized for comprehensibility. But we wanted to just have a feel for what this looked like. There'd be no point optimizing for comprehensibility if it meant that only much less of the code was exercised than if you manually drive the test set. So what we did, we generated test sets of the same size as the W3C test set, which is 280 test cases, and then looked at software called Euclid. We looked at the core functionality of Euclid. So what Euclid does, it takes MathML and it converts it into any image format you want. So we actually chose SVG, and we looked at the core set of Java classes, and we looked at statement coverage. And we found that W3C hit about 61.2%, if I remember correctly. Go test varied, of course, because we generated many test sets, and this is just the median plotted here. And they vary between about 58% up to about 60.2%. So we were 1 or 2 percentage points below the W3C test set. That's not bad, considering that we were putting no other knowledge in there, apart from the specification and optimizing for comprehensibility. So there's some indications that perhaps future work should be to optimize for another objective, which would be coverage at the same time that we're optimizing for comprehensibility. Okay, so in summary, demonstrating extension to our existing Gödel test framework, in this case to automatically generate XML test data given the schema definition. We've used a search method which is prevalent in the gaming community called nested Monte Carlo search to improve comprehensibility of the generated test cases. I've talked a bit about a case study using MathML2 JUpilot. And finally, I haven't really perhaps emphasized this enough. Our existing work in Gödel test very much used abstract data types such as trees. One of the reasons we wanted to do this was to demonstrate that we can use concrete, real-world use data types, in this case XML, and of real-world size. So here we were using a choice model, using a generator which had over 200 choice points, and had therefore a lot of flexibility in how to optimize. Thank you very much.
Questions?
So in mathematics, we define a probability based on the number of trials which approaches to the infinite number. In the Monte Carlo, this number should be a very big number because we are doing this simulation maybe 10 million times whatever. I cannot connect to your method because in this tree, how I can have the big number of tries to trust the result.
This is the surprising fact. So this is the Monte Carlo tree search methods and not our methods. We're borrowing it from colleagues when I was at York who apply this a lot. It's a surprising result. We would have thought that if you're doing simulations, you would want to cover many simulations and take some kind of average behaviors and distribution behavior. Turns out that in a lot of Monte Carlo tree search methods, just doing that one simulation is sufficient. It's not a one-time simulation though, because you then make a choice. Obviously, it's noisy because you've only done one simulation. But then you're going to do a simulation again at the next step, and there's time to correct itself to a certain degree. And it turns out that's often sufficient. There's more sophisticated techniques than the one I'm showing, which are the sort of true Monte Carlo tree search techniques, which do more than just one simulation. Turns out that when you've got a single player game, one simulation makes more sense, but in general you do multiple simulations, and then you use some kind of metric to work out whether you've done enough simulations to make a judgment between choices you look to see if there's a clear distinction. But it turns out that nested Monte Carlo search is just a one simulation. It's surprising, but it gives enough result to guide it. So it's a surprise, but we're taking advantage of that surprise basically, and it turns out to be pretty efficient for doing that.
So, very interesting talk, I enjoyed it. Would you mind going to your slide on the comprehensibility metric or measure? So I'm wondering how sensitive perhaps your results are to this comprehensibility metric, and thought of just a number of things. First of all, there's definitely been studies that show that for software maintainability, that even just lines of code or size might be a comprehensibility measure that correlates with understandability and comprehensibility. But certainly some older, much older measures back in the day, Maurice Halstead and his programming psychology and effort and volume, or even McCabe's. And I just wonder if it might be, I'm not sure if it will give you enough information, but you might be able to look at the XML and say, oh, here's Halstead's notion of constructs and operands and operators and effort and volume, and I might be able to map that somehow to these notions in the XML and just see how it does.
That's a really interesting thought. I mean, we went for something very simple here, but you're right, it's ignoring a lot of the structure. It's doing a simple count. I agree with you. I think that would be a really interesting direction to go. The other piece we're obviously missing is, this is our guess at what the comprehensibility metric is. What we'd like to do is actually put it in front of humans and see whether that really is the case. What is comprehensibility in this sense? But I think you're right. I think there's much more which should be teased out of the structure to make sense of that. One thing we're definitely missing, I'm only talking about structure here, and really, I think one of the big factors will be the actual values you choose. So, for example, when we choose a string, we just choose an arbitrary sequence of ASCII characters. And of course, if it's a book title or something, that's meaningless. So there's another side that we want to do, which is to look at how do you get meaningful real-world values as well as get the structure right as well. I think that's the other aspect of comprehensibility in this case.
Any other comments, questions? All right, so time for speaker again. Final talk this evening by Ouni, and the title is a multi-objective refactoring approach to introduce design patterns and fix anti-patterns.
Okay, so hello everybody. I'm Ouni from Osaka University. So now I will be presenting our research work around the use of multi-objective optimization for software refactoring to introduce design patterns while fixing anti-patterns. So the outline of this talk is organized as follows. I will start by the general context and the research program, then I will be describing our approach. After that, I will describe the validation and the obtained results. Finally, I will conclude and give our future research directions. So let me start by a typical software engineering problem. We all know that software systems are like people, they get old. So over time, they increase in complexity and decrease in effectiveness, so that some changes tends to be made quickly and dirty. They are implemented in a wrong way and making the software system even more difficult to evolve and to maintain. So to this end, there is a high need to maintain a high level of quality of software systems during their life cycle, especially in the case where the original developers are not around anymore. These times, maintaining a high level of quality is highly needed. The most used technique to improve software quality is refactoring, which is defined by Mkaouer as the process of changing the internal structure of the software system while preserving the external behavior. And today, the majority of the modern IDE clients support this kind of refactorings. When applied well, refactoring brings a lot of advantages. It improves software quality and maintainability. It provides a better extendability. At the same time, it increases the speed at which programmers can write and maintain their code. But when applied manually, refactoring becomes an error-prone and time-consuming problem to define or to determine what are the best refactorings to apply for that situation. To design some research approaches have emerged recently to tackle this problem, which is recommending some refactorings to improve software quality. The existing research work can be divided into mainly three categories. So the first category is based on quality metrics, where the goal is to optimize a specific set of quality metrics. Another category is based on the correction of code snags, where the goal is to fix as much as possible the number of existing codes melts into code. And another category tried to improve the code by introducing some design patterns in order to improve the quality, the readability, and the understandability of the code. But all of this existing work presents some limitations because most of them are specific, goal-specific approaches. So, for instance, fixing patterns may affect some other quality metrics, and improving quality metrics does not mean that the existing anti-patterns are fixed. At the same time, applying a design pattern where it is not needed is highly undesirable, as it may increase the complexity of the system. So, as we see, there is conflicting consideration. So, fixing anti-patterns may increase or may affect some quality metrics, improving also quality metrics may affect or may introduce particular anti-pattern types. Also, with the design patterns, we need to make sure that we need an anti-pattern in that situation. So this is mainly the problems with the existing work that are goal-oriented tools. At the other hand, recently there is some empirical study that shows that refactoring techniques are underused by software engineers. So they don't fit all the needs of software programmers because they are goal specific. So this is the main motivation of our work, is to provide a more general refactoring framework that takes into consideration all of these conflicting criteria in order to come up with refactoring solutions that provide a kind of trade-off between all of these criteria. So, to this end, we propose an approach, a search-based approach to find the optimal refactoring operations. Our approach takes as input the source code to be improved and an anti-pattern detector, a design pattern detector, and a quality software quality evaluator in order to evaluate the quality of the software system before and after applying the refactoring. And as output, it recommends the list of refactorings that should improve the software quality while fixing anti-patterns and introducing design patterns. So we are based here mainly on NasBASE2015, which has proven to give good performance in solving many software engineering problems. In general, to train a software engineering problem as an optimization problem, there is some elements that need to be defined, like the search technique. We need to choose the best search technique to apply, and also we need to find the best solution representation and define crossover and change operators, and also to define, most importantly, the objective function. So here, as I mentioned, we are using NasBASE2 as solution representation. We use the vector representation. Here, each dimension is a refactoring operation, and the sequence of refactorings should be applied in the right order. After that, it should be evaluated using our fitness function. So we considered a list of existing refactorings that are the most common by software programmers. In addition, we defined 3 new refactoring operations on, let's say, combined refactorings to introduce a factory design pattern and to introduce visitor and singleton. We are mainly based on 3 design patterns in our approach. So for crossover, we use a single random point crossover. So for 2 solid refactoring solutions, we choose the cut point and display the two parent solutions to have another child solution. For mutation, we use a random, we randomly select one or more dimensions in this vector, which are refactoring operations, and trying to modify them or replace them by other refactoring operations. As objective functions, we have three objective functions. The first one aims at calculating the number of introduced design patterns, as our aim is to introduce design patterns to improve the quality. The second objective function aims at calculating the number of introduced design, the number of fixed anti-patterns. So calculate the initial number of design patterns of anti-patterns over the initial number of anti-patterns. And the third objective function is aims at calculating the quality gain. So calculate the quality, some quality metrics before refactoring and after refactoring to see whether our solution, our refactoring solution, can improve these quality metrics that we want to optimize. To evaluate our approach, we have three research questions. The first one is to investigate to what extent can the proposed approach improve the software quality in terms of quality metrics and design patterns and anti-patterns. The second research question is to investigate how does the proposed approach perform compared to other existing refactoring techniques. And as third question, so we need to see if the proposed approach can be useful for software engineers and can be adopted by these software programs. So we studied, we applied our approach to 4 open source software systems ranging from 245 classes to 1,191 classes. It contains different numbers and types of anti-patterns and also different types of design patterns before refactoring. We are using or we are studying 4 types of anti-patterns, which are the gold class, future MD, data class, and spaghetti code. We also we are also based on the design patterns, the abstract factory, the visitor, and the singular one. And regarding the quality attributes or quality metrics, we are based on the key mode quality mode model, and we use the usability, flexibility, understandability, effectiveness, functionality, and extendability, which are the 6 quality attributes defined within the key mode quality model. To answer the research questions, we conducted the quantitative and qualitative evaluation. For the quantitative evaluation, we investigate whether the proposed refactorings fix anti-patterns and whether it introduces design patterns and whether it improves the quality of the system. As qualitative evaluation, we need to make sure that the recommended refactorings are feasible and can be applied safely to the source code in the sense that do not affect the semantic coherence of the source code. In addition, for the introduced design patterns, we need to make sure that these design patterns are needed in the place where they are recommended and not arbitrary changes or arbitrary recommendations. To evaluate the approach, we compared with mainly 3 existing works. The one of Sank in 2006, who tried to optimize 11 quality metrics, and we compared it also with the work of Jensen in 2010, where he tried to improve the quality of the system by introducing design patterns using NasBASE approach. And finally, we compared it with the work of Kessentini in 2011, where the main goal was to reduce the number of anti-patterns in the source code. So here is the obtained results. Our approach is more and compared with the three other approaches. And as we can see, there is a kind of compromise between all of the objectives. So we found a kind of balance, as we can see here, for instance, for NP, which is the number of introduced patterns. This is the average of the four systems. We obtained, we successfully introduced seven design patterns, which is less than the one of Jensen, who successfully introduced 20 design patterns. But in terms of compromise, we see that we have significantly better results in terms of ACR. We have 86%, while Jensen has only 21%. And also in terms of quality gain, we see that approach provide better results, 0.37, while the one of Jensen obtained only 0.35. So as we can see, there is a kind of trade-off that should be obtained when recommending software refactoring. So here's the results for the quality gain and the 6 quality attributes for Q-mode. We found that we successfully improved most or all of the quality attributes. For instance, the understandability was the best quality attribute, which is improved, and this is mainly due to the introduction of design patterns and fixing anti-patterns that mainly enhance and improve the understandability of the system, but at the same time improve all the other quality attributes. So here is the results for the qualitative evaluation. The criteria refactoring meaningfulness, which calculates the number of feasible refactorings over the total number of recommended refactorings. We found that our approach provided much better results than the other three approaches, and this is mainly due to the semantic constraints that we define, and also because we consider all the criteria and not only one criteria like other approaches which are goal-oriented. So our approach is more general and takes into consideration the majority of the needed criteria or the expected benefit of refactoring. Regarding the design pattern usefulness, we found also better results. We compared in this table our results with the one of Jensen, because this is the only approach that uses SDSC to introduce design patterns. We found that most of the introduced anti-patterns of the introduced design patterns are useful for example, for exercises. We found that 83% of the design patterns are useful, while having only 55% for Jensen. And this proves that our approach is more practical and more useful for software programmers if they need to introduce design patterns. So also there is a high need in software engineering to provide scalable software engineering tools. To this end, we investigate the scalability of our approach. So this figure shows the execution time with respect to the size of the systems in terms of number of classes, and we found that the execution time is relatively stable with software systems with different sizes, and this shows that the approach is relatively stable from the scalability standpoint. So to conclude, our goal was mainly to introduce a more generic refactoring recommendation tool that considers many criteria unlike existing tools that try to optimize specific criteria. We considered mainly three criteria. The first one is to fix anti-patterns, to introduce design patterns, and to improve the overall quality of the system. We conducted an empirical study on 4 open source systems, and the obtained results are promising. So now, as future work, we are trying to include other types of anti-patterns and other types of design patterns within our approach, and we want to test it with other industrial software projects. Another thing which is very important in SBSE in this program in particular, which is the developer, so we need to include him in the loop. We need to take his feedback in order to provide or to come up with better results that fit his preferences. So as future work, we are planning to propose an interactive factoring approach where the developer is the main component in this approach. Thank you for your attention.
So maybe if you look at slide 15, I really enjoyed your talk. And slide 15, and when I was thinking about you comparing to the Jensen study, and by the way, I liked how you compared to their study, and that made it, I think, more meaningful and put it in context. But when I saw this slide here for Jensen, and I saw Antipachi and Xerxes J, I thought, they've retrieved 28 and 31 patterns. That seems maybe like they're throwing the kitchen sink in there. And it made me think of some of our traceability studies where folks might be optimizing recall, but not worrying so much about precision. And it just made me wonder if you all ever use the measures recall and precision as opposed to some of these other usefulness measures.
Actually, yes. So here we are not using precision or recall. So here we are dealing with recommended refactoring. So here we recommend, and Jensen also is recommending some refactoring operations. So Jensen is going to randomly generate some refactoring solutions. At the end, he calculates the number of introduced design patterns. He don't have any constraint or any preferences. His goal is mainly to introduce design patterns without considering other criteria, even if he increase the complexity of the system, or even if he introduces design patterns in a place which is not needed. So this is highly undesirable, and it's not good to. For us, we are guided by another objective function, which is the quality. So this is as a constraint. So if I introduce a design pattern in a place, and I increase the complexity, or I increase the coupling, so the multi-objective process will reject the solution as it's not optimal. So to this end, our approach performs better than Jensen.
Because we found also in general, when we introduce too much design patterns, your design become more complex than the initial version. So it's,
in your experiments, you try 3 design patterns. There are other design patterns as well. So is there any specific reason that you did an experiment with?
Yes, so as the first prototype, we tried to prove the feasibility of the approach. And you know that automatically introducing the design pattern in the source code is not as easy task.
Yeah.
Even for the developer, he needs to understand the semantics of the code and decide where he can introduce the design pattern. So as a first prototype, we focused on these 3 design patterns, but now we are trying to add other design patterns to show in more generic way our approach, how it works. So yeah, it's interesting to I mentioned that in the future work. So now actually we are trying to define some transformation for 2 other design patterns, and also we are including some other types of anti-patterns also. Okay.
Any questions?
Maybe, can you maybe think about the intuition behind their work? So why do you think that maybe using design patterns as an objective with fixing anti-patterns as our objective can perform better than existing approach? Because I do believe that maybe before selecting what are the objectives of your multi-object algorithm, we need to have maybe an empirical study that maybe try to understand the correlation between design pattern and design anti-patterns. To the best of my knowledge, I'm not aware of studies that try to study the correlation between introducing design patterns and fixing anti-patterns. So maybe some specific design patterns that are introduced how to fix some anti-patterns. So, and here you can justify the use of the two objectives.
Yes,
So,
here in our experimental, we found some cases where a visitor design pattern is introduced within a block class. So here the visitor can reduce the charge within this block class. When we want to add new code to this class, we just add it to the visitor and we don't touch the block class. So here we can reduce the charge or to this block class by this anti-pattern. But our ambition at the beginning, our motivation was to introduce more generic framework for refactoring, because now most of the tools are goal specific, and recently there is a study by Murphy, so showed that refactoring is underused, so programs are not using refactoring as expected, and I think so there is something missing with the existing tool, because they try just to optimize a particular part of the system and they do not provide so generic framework that fit for the needs of all the programs. And I think if programs found more generic tools, so they will take benefit of refactoring more than the actual situation. So this is the main goal behind the performance.
I guess that two examples that you mentioned about the visitor, how it can help to fix a block, is really a good example to show the need to have these two objectives.
Yes.
So I think this fits well with my normalization idea that I talked about. So some of these patterns and anti-patterns can be obtained as an innovation study on your non-dominated set of solutions that are forming. So if you can detect early these non-dominated set and what is common in those solutions, that they can go as patterns, and those that are not there in this set, but it's there in the rest of the dominated set, and act as an anti-pattern or something. And so identifying those patterns and anti-patterns, and then putting them now applying them as you're going. So this can change. So at generation 50, you identify these patterns, anti-patterns. Generation 75, you've got some other patterns, anti-patterns. But as you're approaching the front, if you identify and fix it, I think there are faster convergence.
Oh, it's very smart. I think we should see what we can obtain with that. It's very smart.
We're trying to do it on some design problems, actually. So helping SDA2 with the innovation principles, so it's converging faster than
I think
can use it.
Yeah, try innovation. I think it should be a very smart idea to improve what we obtain now. Try to consider that. Probably we can extend this paper using innovation.
Yes, and actually what you can do, you can use innovation to extract some features on our refactoring solution and see if these features correspond or not to some design patterns. Some unknown design patterns correspond to some features maybe in your refactoring.
That's very interesting. Thank you for this.
Okay, any other comment, question? It's the end of the day now. So do you have any?
Oh yes, we have a dinner at 7:15. It will not be in the room next door, but it will be in the restaurant near the lobby. So you can go to the lobby and ask for the dinner room. So it will start at 7:15. Yeah. So see you later.